Just in case we can't have class, I thought I'd record this overview for choosing the right hypothesis test. This is a handout that we were going to do in class if we hadn't had class. The first question, we'll get right to it. It's asking for us to do hypothesis test selection. We're just trying to choose a hypothesis test. We're not trying to do the hypothesis test in this review. So the first question, we're going to look for some key words. It's asking a question, do male and female students study the same amount per week? It doesn't ask average or variance or anything at this point. It talks about a study that happened. It gives us N. It gives us where they were surveyed, large university. It tells us that the university has more than 1,000 students. That really doesn't matter. But then it asks us the specific hypothesis test. It says, is there a difference in the variance of the study time for male students and female students? If you're reading it and you're nervous, you're probably very likely going to skip the key information. And really it's just asking, is there a difference? So we know it's going to be equals and not equals. That is the differences. We know that HO is going to have the equality. H sub 1 will have the inequality or not equals to. And since it's asking the variance, it's asking the variance of study time for male and female students. So it looks like it's comparing two different samples. And so there's going to be a variance on one side and a variance on the other side. Obviously it's got to be squared for variance. And then one of them is going to be for male students and one of them is going to be for female students. But remember that when we're doing a variance test, we always choose the higher variance first. Quick reminder. Higher variance first. Just so you remember. But there's your hypotheses. Hopefully you got those. The next one. U.S. Department of Education reports that 46%. All right away I see that there's a proportion. So it's going to be some kind of a proportion. In fact, let me switch colors really quickly. Switch to green. We have a proportion listed right away. Proportion, and I wrote sample proportion or population proportion. It says that the U.S. Department of Education reports that 46% of full-time college students are employed while attending college. And then a recent survey of 60, so we know that this one up here is the population value. And now a recent survey found that full-time students at Miami University, 60 of them, so if I'm remembering, if I'm looking at proportions, I need N. That's going to be N. And it says here at Miami University found that 29 were employed. So that's an X. So clearly this is a proportion test. It even asks, in that very next, is the proportion of working full-time students? So, and it asks different from the national average. So we've got a proportion and a proportion. Our H null is focused on the proportion, and it says is the proportion of full-time students different from something? So difference again is equal to or not equals to, and it asks equal to different from the national average of 0.46. So just put a 0.46 there, 0.46 there, and there is my hypothesis tests. Let's scroll down a little bit and do number 3. Switch colors again to red. You're the manager of a restaurant that delivers pizza to a college dormitories. You have just changed your delivery process in an effort to reduce the mean time between the order and completion of delivery. So there's a difference in the mean. We know that we're looking at mean here, and looks like there's a current value, currently 25 minutes as a mean. We took a sample of 36 orders using new delivery, And so we've got a sample. We've got n equals 36. We know that our population mean is going to be listed below. We have a sample mean and a sample standard deviation. That's important because we don't have a population standard deviation. So we can write that now. Sigma unknown, which means the population standard deviation is unknown. And I know x bar equals 22.4. The sample standard deviation is 6 minutes. And so then it asks the question. That's just the information that we have up to this point. The question asks, at the 0.01 level of significance, is there evidence that the population mean delivery time has been reduced below the previous population mean value of 25 minutes? To me, that's very clear, but if it's not, let's walk through it. We're given alpha very first, so we know alpha is 0.01. We know that it's asking about the population mean, so I know my hypotheses are going to have the population mean in them. And it says, has the mean time been reduced below? Reduced, it means less than. And so that means basically less than, in quotes, below the previous population mean value of 25 minutes. So we're comparing, or we're testing to see if we've changed against that. So less than would be the second one, and the opposite would be in the null. And there's my h sub 0, there's my h sub 1. And this is going to be, since sigma is unknown, that means it's going to be a z, it's going to be a t-test. And that's the information that we've got. And we could actually do this test completely with the information that we have, but we're going to move on. So that's number 3. Now let's look at number 4. Number 4, there it is. Alright, so number 4, change colors again. A study conducted in March found that about half of U.S. adults trusted the U.S. government. Half, let's just slow down, half is really a proportion. It's a percentage or a proportion. Half U.S. adults trust the U.S. government more than business to solve the economic problems. However, when the population is subdivided by political party affiliation, the results are very different. Studies showed, here's another proportion, 72% of Democrats trusted the government, and 29% of Republicans trusted the government. And so those are clearly two different groups that we're looking at. And let's go on. It says, after taking a national sample of Democrats and a national sample of Republicans, clearly there's a sample and there's a sample. So we're doing a 2-sample test. 2 samples. Of course, we got to wait till it asks the question to really know. It says, we want to try and use the results to show statistical evidence that the proportion, look at that nice giveaway, proportion of Democrats trust in the government, so we'll do proportion D, proportion of Democrats, we'll reference that by pi sub d, and that's going to be compared to the proportion of Republicans. Here's our hypotheses right here. So I know that I'm comparing these values. See if I can make that look a little cleaner. Proportion, and also there's a keyword here. More than business, that's not the keyword. The keyword here, Democrats trusting government more than business is greater than, there's the keyword, than the proportion of Republicans trusting the government. And so that's going to be Democrat greater proportion than Republican. So that's going to put a greater here and a less than or equal to there. And so our null is on the top and our alternative is on the bottom. And since it's a proportion, we know it's going to be a z-test. And it's going to be a right tail z-test. And so that's number 4. We probably have enough information. Looks like we've got the sample proportion there. So, yeah, we got enough information. We could do that one. All right, number 5. Marketing manager of a branch office of a local telephone operating company wants to study characteristics of residential customers served by her office. In particular, she wants to estimate the mean monthly cost of calls within the local call region. Estimate the mean monthly cost of calls. So there's a giveaway. The mean monthly cost of calls. In order to determine the sample size necessary, she needs an estimate of the standard deviation. On the basis of her past experience and judgment, she estimates that the standard deviation is equal to 12. See, now here's one where it's not going to be on the test, but we'll go through it anyway. Suppose that a small-scale study, notice that we're talking about standard deviation. Suppose that a small-scale study of 15 residential customers indicates a sample standard deviation of 9.25. At the 0.1 level of significance, so we've got, gives us a level of significance, that's our alpha, 0.10. Is there evidence that the population standard deviation is different from 12? And like I said, this won't be on the exam, but just reading through it, it's very clear what's being asked here. There's a single sample. We're focused on the standard deviation, so the hypothesis will be referring to standard deviation, or sigma. And your sigmas are probably nicer than mine. But is different from $12. So different from means equals and not equals. That's what different means. So the alternative is the population standard deviation different from $12, or the null would say, is it the same? And so that is a one sample test for the standard deviation, which we didn't cover in class because the book moved it to an online chapter. Such a shame. But don't worry about number 5 for the exam. Alrighty, moving on to number 6. There it is. Number 6 says, 4 experts rated 2 brands of Colombian coffee in a taste testing experiment. A rating on a 7-point scale is given for each of the 4 characteristics: taste, aroma, richness, and acidity. The following today display the ratings accumulated over all 4 characteristics for each of the experts. So I see row labels. That means that brand A and brand A ratings both belong to expert with initials CC. So if that's the case, I'm probably looking at a paired sample test for means, but let's see what happens. I'm just going to write a little note here. Usually means paired t-test. For mean difference. Since I've got row labels, and you can see that there's a row label on each one of the rows. So the question asks, with this data, at the 0.05 level of significance, we have alpha. Is there evidence of a difference in the mean ratings between the 2 brands? Difference in the mean ratings between the 2 brands. All right, and since this is a paired t-test, where you're looking at the mean difference as a population value, and so our hypothesis will look a little bit different than the other 2 sample tests, but it is a 2 sample test. We're referring to mean difference, mu sub d, and it's asking, is there evidence of a difference? And so again, it's equals and not equals, and the mean difference If there is a difference, the difference would be not equal to 0. If there isn't a difference, the mean difference will be 0. So that is our hypothesis, and it's a paired t-test. And the formulas are in the book, so that's pretty neat. It's a pretty easy one. All right, switching colors again. Number 7. The American Society for Quality. It's a good group. You should join them. They conducted a salary survey of all its members. ASQ members work in all areas of manufacturing and service-related institutions, with a common theme of an interest in quality. 2 job titles are green belt and black belt. All right, I'm starting to smell a 2-sample test. Green belt and black belt. Assuming the population variances are the same for the 2 job titles, again there's 2 sample, and it says assume population variances are the same. So I know it's going to be, I'm assuming, oops, I probably shouldn't write it there. I know that sigma 1 squared equals sigma 2 squared. So that is something that we know. We're given use a 0.01, so alpha is 0.01. 0.01 level of significance to test whether green belts earn less on average. Less is important and average is important because we're testing whether green belts earn less on average than black belts. So the average means I'm going to be looking at the mu. Since it's a 2-sample test, remember this number up here, it's going to be compared 1 sample. In fact, I'm going to write GB on one and BB on the other one, green belt and black belt, since that's the focus of the study. And it says whether green belts earn less on average, and since mu green belt is on the bottom, on the left, we should put it like this, so that it's showing less than, mean of the green belts is less than mean of the black belts, and so the null would just be greater than or equal to, or the opposite. So there's H0 and there's H1, and those are my hypotheses. And I should also list the kind of test that we would do. We know it's a left tail test because it's mean of green belt less than mean of black belt. And we should note that this is a 2-sample pooled variance t-test. And so that is the answer to number 7. All right, lastly is number 8. Stationery store wants to estimate the mean retail value. Let me change pens because I'm already seeing keywords here. The mean retail value of greeting cards that it has in inventory. It wants to estimate it. A random sample of 100 greeting cards. So we've got a sample of 100. I know n is equal to 100. I like to write things down that I see. A random sample indicates a mean value of 255. So I know that the mean or sample mean is $2.55. It just listed that. It just told me that. Based on historical data, they can assume the population, look at that, population standard deviation is 0.44. So I know that the population standard deviation equals 0.44. Also, since we know it, we could say sigma is known. Looks like a z-test to me. But let's read on. It says, is there evidence that the population mean retail value of greeting cards is different from 250? So for reading that, we know that we're going to be testing the mean. Different means equals and not equals, and it's compared to 250. And so there's my H sub O and my H sub 1. And it's going to be a z-test for mean. since we know the population standard deviation. That keyword there is population. Z-test for mean. And it's one sample, obviously, because it only lists the one sample, a random sample. See? One sample. Probably can't see any of those. Looks like they're off screen. All right, so that is the appropriate answers for the review sheet. If you want to practice doing some more, I've got some more review sheets online. But I thought I'd walk through that just in case we don't have class, so you can feel like you're more comfortable going through and choosing the right hypothesis for each of these. All right, have a good evening, and I will see you on the day of the test.